Hi, it's Dr. McFerrin from DM Explains. In this video, I'm going to talk about how to model electromechanical systems using the Laplace transform. Electromechanical systems are the combination of electrical and mechanical dynamics. These include mechatronic systems, motors, generators, and a whole host of other types of systems. One thing that we should note is that typically electrical dynamics happen much more quickly than mechanical dynamics, so sometimes we're able to ignore our electrical dynamics. To help us understand how we will model electromechanical systems, I'm going to work through one big example and we'll talk through it as we go. In this example, I'd like to find the transfer function of a DC motor. The transfer function I'm looking for is theta m of S over VA of S, and the motor is going to be modeled using a circuit. So here's what it's going to look like. I've got a resistance RA, that's my armature resistance, and then I've got an inductance LA, my armature inductance, and then I'm connected to a rotor, and the input voltage here to this armature, or measured voltage across the armature, is VA. There is a current IA of T which goes through this armature, and let's say that the voltage across the rotor is VB of T. So this side is the armature. The rotor possesses some mechanical parameters. It has a torque, which I'll call Tm of T, and it has theta, which is an angular displacement, theta m of T. And then there's also field windings for this motor. So we represent that using an inductor, LF. So this is my field, or my stator. The solution we're looking for is the transfer function, which I'll call G of S, which relates the input VA of S, so an input armature voltage, with theta m of S. That is the angular displacement as a function of S. To start, we're going to use some rules from electromagnetics. There is a back EMF, electromotive force, generated by the motion of a rotor in a static magnetic field. That's VB of T, the voltage across that rotor. It's equal to K sub B d theta m of T dt. V sub B is my back EMF, and K sub B is the back EMF constant. Then VB of S is equal to K sub B times S theta m of S. I'm going to call this equation 1. I'm going to circle back to use it later. I found this just by taking the Laplace transform. Because I'm finding a transfer function, I know that there are zero initial conditions, so the derivative of a function converted to the Laplace domain is just S times the Laplace version of that function. The relationship between armature current, IA of T, and the applied armature voltage, VA of T, and back EMF, VB of T, can be found by using Kirchhoff's voltage law. All right, so a little bit of circuits knowledge is needed here. I look at this circuit here. I've got negative VA of T is the first thing, negative VA of T. And then I come across this resistor. The voltage across there is RA times IA. In this inductor, I've got LA times the derivative of that current, and then I've got plus VB. So let's put that all together. So I've got plus RA IA of T plus LA DIA of T dt plus V sub B of T equals 0. And then I can take the Laplace transform of this and move VA of S to the right-hand side. So I'll have RA plus SLA times IA of S plus VB of S. What I have right now is an expression in terms of VA, VB, and IA. I know what VB is from equation number 1, but I want an expression which is not between VA, IA, and VB. I want an expression which is between VA and theta M. So I'm going to need more information. The first bit of information we'll have is that the torque in the rotor is proportional to the armature current. That means that Tm of S is equal to some proportionality constant, Kt, it's our torque constant, Ia of S. They're proportional, which means that Ia is equal to 1 over Kt Tm of S. Let's call that equation 3. And then what I'm going to do is I'm going to plug equations 1 and 3 into equation 2. We'll get ourselves a little bit closer to where we want to be. So I've got this. I've got Ra plus SLA times 1 over K sub T Tm of S plus VB, which I found to be KBS theta M of S, KBS theta M of S, is equal to VA of S. Now, if you remember, what I'm looking for is a relationship between VA and theta M. So I'm almost there. I just need to find a way to get rid of this torque. To get rid of the torque, I need to use rotational mechanical dynamics. I know that this rotor, let's assume that it has some amount of damping. Depending on its value, this could be 0 or something else. And let's also assume it has some inertia. So let's give this a damping constant. Let's call it d sub m. And let's give the inertia a constant j sub m. And then I've got my theta m and Tm here. And I know from rotational mechanical dynamics that Tm of S is equal to Jm S squared plus Dm S times theta M of S. It's the sum of the impedances, in this case an inertia and a damper, multiplied by the angular position. Let's call this equation number 5, the previous equation number 4, and then I want to sub 5 into 4. When I substitute 5 into 4, here's what it will look like. I'm going to end up with SLA plus RA times JM S squared plus DMS. This is all multiplied by 1 over KT plus KBS, all times theta M of S is equal to VA of S. Now we have this entire expression in terms of VA and theta M. Before we put this into a transfer function, let's make one assumption. Let's assume that LA, my inductance in my armature, is small compared to RA. This happens to be true for most DC motors. And so what happens is that in this expression, RA dominates the value. And so we can eliminate SLA. Then I'm also going to pull out an S. So this is going to put me at RA over KT times JM S plus dm plus kb all multiplied by s, theta m equals to v, and that's theta m of s, equals to va of s. Now, if I multiply kt by both sides, I can find that theta m of s over va of s is equal to kt over ra times jms plus dm plus kb kt all multiplied by s. I can simplify by pulling out jm and ra, and so I'll be left with theta m of s over va of s is equal to kt over ra jm over s plus 1 over jm dm plus kt kb over ra. Now, this form looks strange, but if I look at it closely, g of s is really just some constant k over s times s plus a, where a is equal to 1 over jm dm plus kt kb over ra, and big K is kt over ra and jm. This is a simple form, and it's actually not hard to find these constants for a motor. Now, if I want to find the constants, I can attach a load to my motor, and I can use my rotational mechanical systems dynamics to figure it out. To do the electrical, I can find the stall torque and the no load speed and use that information to get some of my constants. I do this using a dynamometer. But for now, what we've seen is that we can in fact simplify a motor into an expression which looks like a transfer function. And really the transfer function, even though it's strange, looks pretty easy to deal with. That's all I have for this video. So until next time, thanks for watching.